Hey there, students, and welcome back to week number 4. In this week's class, we'll be talking about the equal sign, and I have a brief presentation that I'm calling Variables, the Equal Sign, and Technology. Oh my! So just as a quick recap, from the readings on variables, we had a few big ideas. One of them is that students have multiple pre-existing ideas about variables before they come to our class. For example, my 3-year-old has a little toy, and that little toy always says A is for apple. And so she learns that the letter stands for a thing that starts with the same letter. And we see this idea very often in math classes where students think that the variable has to have the same letter as whatever quantity is describing. And as we know, that's not always the case. In fact, sometimes very counterintuitively we use variables that have no relation at all to the, we use letters that have no relation at all to the thing we're describing. So we use M for slope, even though the letter M shows up nowhere in slope. So second thing is that many of these ideas that students have are not random. They're rooted in prior experience. And one of the examples from the reading from the Australian study was that students were doing strange things like writing 10H for 10 less than H. And at first the authors were confused until they learned that the students had learned about Roman numerals, where we write 1x or ix for 1 less than 10. And so it makes sense that you might write something like 10b to be 10 less than b. And then the nice thing is that these conceptions can change with instruction, so they're not necessarily a sign of innate intelligence or a sign of kind of students' future trajectory. This can change over time, which is encouraging. And at the same time, we also have this caveat from Randy Phillips' article that, in fact, the way that we use literal symbols, so letters and variables and even symbols, to represent quantities, is different depending on the context. So sometimes we mean that a letter is a missing number, sometimes we mean that it's a varying quantity, and sometimes we mean that it's a constant. It's never going to change. And so for students, it might be a little bit confusing that we're using the same things, these letters or literal symbols, but meaning different things. So we need to not necessarily do anything different, but really think carefully about how it is that students are thinking about the symbols that we're writing on the board. Alright, so this week you also read a couple of readings about the equal sign, and much like the literal symbols research, students have really different ideas about the meaning of this equal sign. One of these ideas is called the relational idea. This is kind of the conventional meaning, which is that there's a relationship or a balance between the two things on the left-hand side and the right-hand side of the equal sign. And what I have right here is a little activity that is designed to teach that idea, showing that whatever's on the left-hand side is supposed to be equal to the right-hand side. And there's a little bit of algebra in this problem, actually. Second grade problem, by the way. The second meaning is the operational idea, which indicates that there's an operation to be performed, something to do. And what's interesting is that we might think that that's a pretty obviously incorrect idea, but if you look carefully at your calculator and just pull out the nearest calculator you have, chances are that on that calculator, this little equal sign means go, or calculate, or do whatever I just entered. So in fact, this idea is utterly rational and growing out of students' prior experience. And again, I think that these ideas, these relational understandings, rather than the operational understanding, can be developed through various activities in elementary and middle school mathematics. So that shows that there's a role for us as teachers in helping students develop an understanding of the equal sign. And from the Knuth paper, we also saw that students who have a relational understanding of the equal sign are more likely to be successful on solving algebra tasks, which stands to reason if you think about in all algebra tasks, we usually mean the relational meaning of equals. So in this little video, part 2 here, I want to just take a few minutes and show you how this plays out in technology. And it's rather interesting because technology actually requires us to use the equal sign in the different ways and to use variables for different purposes. So as you, as future teachers, might want to think about some of these technologies that you're going to be using, I thought I'd start off with the one that we'll all use, which is probably Desmos, the graphing calculator. It seems that Desmos is like the TI slayer. It's putting the TI-84 out of business and replacing these devices with the Desmos online graphing calculator. A number of folks for years have been saying, hey, students should be using spreadsheets. Spreadsheets are practical, they're everywhere, incredibly useful. Let's use them more often. So I want to show you a little bit about how spreadsheets handle the equal sign and variables. Now, if you're moving into statistics, you probably have heard of R, which is a statistical computing software. And R does some rather interesting things with variables as well. It's also free, so that's a nice bonus. And I'll show, just for the fun of it, a little computer algebra system called Maple. I don't think it's very likely that you're going to be using Maple or Mathematica in your teaching. However, these algebra systems exist, and in fact they're built into the TI-92 or 89. And it's interesting to think about how they use the equal sign slightly different as well. Let's take a look. So what I'm going to do is go into each technology and we'll do 4 main things. Create a variable, that is assign it a value. Multiply 2 variables together by writing them adjacent and then using parentheses and seeing what happens. Check if 2 variables are equal to each other. That's looking for a true or false statement. And then in Desmos only, I just want to show off kind of an interesting thing about the difference between variables and constants and some of the ways that Desmos, in order to be helpful, takes kind of a shortcut on you. Let's take a look. Let's start off with Desmos. If I can find my window at Desmos, I think I closed it. Let's go over there. So Desmos is desmos.com. Click on the graphing calculator. Here it comes. And this is the basic screen. If you want to type in any calculation on the little entry window, you type it. 1 plus 1 is 2, and the answer shows up. It is a graphing calculator, so if you type in something like y equals x squared, it will assume that you want to graph the equation y equals x squared in the graphing window, and that's the graph that shows up over here. So for today, I'm not looking at the graphing calculators per se, but I want to look more at the creating variables. And so in Desmos, I can write a variable by saying a equals 2. And when I do that, what I'm doing is I am assigning to a the value of 2. So in the next cell, if I type in, for example, a cubed, the output is 8. And these 2 cells are linked, so if I change the assignment, if I make a equal to 6, then a cubed updates and is now 216. So these 2 cells are linked together. So whatever value of a is here, a cubed is going to give me that value cubed. If I delete the assignment, then a cubed doesn't have an answer anymore, and it simply says add a slider for a. It wants me to put in an assignment for a. So that slider is a way of assigning a value, and by default it'll initially assign the number 1. And the slider allows you to change its value by dragging, which is nice and very convenient. But interesting to think about that we've now changed this static number into a dynamic number. So interesting to think about that relationship right there. I can create a second variable. Let's make b. Make b equal to 4, and I should probably, 1 is a terrible number to start with. Let's make a equal to 6. And one of the things that you always want to do with variables is add or subtract or multiply, and for the most part, addition, subtraction, and division work as expected. However, the multiplication is an interesting case. So typically on computers, we want to write a times b. And oh, by the way, on Desmos, if you show the little graphing calculator, you can actually show the tools here, and I could actually type in a times b. Obviously, that's a little bit clumsy to do that with my mouse. So easier on my computer to do that with my keyboard. Okay, so that works as expected. 2 other ways that we often write a times b in algebra is we might just write a and b side by side. And notice that Desmos is happy with that. It says ab is equal to 24. So ab is a times b, 6 times 4 is 24. And the last way that we might multiply two numbers together is a, b. Oops, excuse me. And again, Desmos works. And this is kind of interesting. So notice that a is a number. It's 6. If a was a function, then we would be evaluating the function a at the value of b, which is 4. And so just to mess around a little bit, let's make a function. So instead of making a equal to 6, let's make a equal to, or a of x. And now we've just changed the type of thing that a is. So now ab is not, in fact, 3x plus 2 times 4, but is 3 times 4 plus 2. So notice that Desmos is doing a lot of work for me in the background. In other words, it says, oh, a is a number. Okay, when you type a parentheses b, that means that you want a times b. But when I change a into a function, now suddenly a cubed doesn't make sense anymore. So it says try using parentheses. ab doesn't make sense anymore. But a parentheses b does make sense. So I'm showing you this as a warning because we just changed the type of thing that a is. And when we did that, Desmos tried to help us out, but it also introduced errors. And so it allows you to be kind of quick and loose with your data types if you study computer science. One last thing on this note is that Desmos is rather interesting that you, as I showed from the very beginning, you can graph a function y equals x. And it's actually very forgiving. You can type in y equals a, and it graphs it. It says, oh, okay, this must be your a axis, and this must be your, this is your a axis, and this is your y axis. Sounds good to me. Y equals b. Oh, this is my b axis. Here's my b axis, and here's my y axis. Oh, keep going. C looks good. D looks good. E. Well, that's weird. F, that looks good. G looks good. Okay, what happened to E right there? And notice right now that this is this idea of a constant. When I type in y equals E, the calculator says, oh, E is 2.71828182846. So therefore, you're actually asking me to graph the horizontal line y equals 2.71828184286, etc., etc. So Desmos, again, treats E as a protected variable. And so this is just an interesting idea. This variable is no longer a variable. Everything else, A, B, C, D, F, G, H, those are all variables. They can vary. But E is a constant. E is the number 2.718, the base of the natural logarithm. Okay, so that's my Desmos introduction. Let's take a look now for something completely different, as they used to say on Monty Python. Oh, I don't want it. It says, do you want to save your changes? No. Adios. Let's take a look at a spreadsheet. So spreadsheets, you may be familiar with, are organized based on rows and columns. Columns all have letters, A, B, C, D, and so on. And the rows all have numbers, 1, 2, 3, 4, 5, and so on. So in a spreadsheet, it works basically as a table, but each table is a cell, and each cell, or each of these intersections is a cell in the table, and each cell can really act as a variable if you'd like it to. So, for example, I could type in 3 and I could type in 4, and then in this cell down here, I could type in an equation using these two cells, cell A1 and A2. And the way you type in a formula or an equation or some kind of calculation is you start with the equal sign, and notice this is a really different use of the equal sign. I guess it's kind of the operational idea. We are saying I want to calculate something, and then what I type in here is I type in 3 plus 4, and the output comes out. 3 plus 4 is 7. So that's what I found out right there. These are dynamically linked, much like they were in Desmos. So if I change cell A1 and make that 9.5, oh, excuse me. I typed in 3 plus 4. Let me try that again. If I type in equals A1 plus A2, now these things are linked. So now I'm referencing not 3 plus 4, but actually referencing the value in cell A1 and the value in cell A2. And you can see that right there. And if I change this back to 3, that goes back to 7. Whew. All right, so you caught me. I was going too fast. When I want to multiply two things together, I have to be a lot more careful in a spreadsheet. So if I want to multiply these, I'm going to type in equals A1 and then times the little star, which is shift 8, A2, and it'll give me the multiplication. If you use parentheses, it will give you, let's find out, an error. It'll say, I don't know what that is. Similarly, if you write them adjacent, I believe that will also cause us a problem. Now, this one's a little bit of a trip, but in a spreadsheet, one thing you often want to do is to know whether or not two cells are equal to each other. And so you can actually type in equals A1 equals A2. Now, this looks like a run-on sentence, but in fact is a Boolean statement. And so it says, the formula I am entering is, does cell A1 equal cell A2? And the output that we're getting is false. If we change A1 to 4, then this output turns into true, because now A1 is equal to A2. Oh, and of course you have to make sure that your data is of the same type. So if we type in something like Chuck Norris here, we're going to get a false answer on that, are they equal? And we're going to get a value which is saying you're trying to add a string to a number, and I can't do that for you. So in the spreadsheet, this is just how the variables are handled. I guess one other thing you might want to know is that in a spreadsheet, you don't always have to use the cell reference. You can actually name a cell. And the way that I always do this, I just right click and go into define named range. This little thing will pop up, and I might call this my apples. And then if I want to define another name range, I might call this bananas. And then I could type in a formula, which is I want apples squared minus bananas. And it's going to use the defined names that I gave over here. Clearly with apples and bananas, this is not very useful. However, if you have something like a spreadsheet modeling a situation with, say, a down payment and an interest rate and the term, it can become much more convenient to name those cells, and then the reference to them is stable. So that's naming the variable. Notice that I can name my variables here using multiple letters. I could use whole names if I want to. In Desmos, that's not possible, because with Desmos, it would interpret this as A times P squared times L times 2.718 times S. So think about how these different programs are going to work together with their naming conventions. Okay, let's move over to R. So R is a statistical workspace. It's mostly used by people who do data science or statistics. But it's becoming more and more popular in high schools because it's pretty powerful and it's free, which is pretty exciting. I'm using a program called RStudio. So if you buy you don't buy, you just download the basic version of R. You just get the console. If you are doing a lot of work in R and you have variables defined, then you can actually pull up RStudio, which shows you your environment and your code and whatnot. So it's kind of a nice way to track your work. So in R, I can do the same thing. I can define a variable. The conventional way to define variables in R is actually to use the assignment code, which is A gets assigned this value of 3. And now if I type in A, output is 3. And I can say B is assigned 4. So notice that in R, at least conventionally, we should be using the assignment code, which is this little backwards arrow which says take the value on the right and assign that to the symbol on the left. And same thing, that we can give our variables long names, short names, whatever we want. We could define our apples as 3, and that will work here. R works much the same as Desmos in terms of how it handles the variables. In terms of, kind of both a hybrid of Desmos and GeoGebra. So I could do, for example, A times B, and that'll work. If I write AB as adjacent, or A parentheses B, it's going to have a problem because it's looking for that function A of B. So again, where Desmos just said, oh, you probably mean A times B, and solved the problem for me, a program like R is going to say, you need to tell me whether you want to do a function or you want to do multiplication. Isn't it funny how we don't think about these subtleties in the notation until we start using a computer? In R, one of the interesting things is that you can do assignment with single parentheses, or single equal sign. So I could say that A is equal to 4, and that'll work. So I updated the value of A to be 4. And B, I think, is still 4. And I can check if A is equal to B. But here, I want to do two equal signs. If I do A equals B, let's try B something else. If I make B 7, and then I type in A equals B, what happened now is it just reassigned A to be equal to 7. So there's a difference between assigning something and checking whether or not it's true. And in computer programming, we often use two equal signs, or at least in some versions of computer programming, we use two equal signs when we are asking, are these things equal? And then we use one equal sign when we're assigning values. So again, it's interesting to think about the meanings of the equal sign and how the computer program is forcing us to be specific on what we mean. But in conventional everyday life, we often go between these two meanings, assigning a variable versus checking whether things are true. All right, for the last tour, I thought we'd take a look at Maple. Maple is pretty amazing. If you've never used Maple, you should check it out. I believe that we have a site license at San Diego State, and if not, then we definitely have it on campus, which you can telnet into or log in. I just marked my age, which you can VPN into. So you can go onto campus through VPN and access this if you would like to. Maple is a program that does all sorts of fun things, but it works much the same as R or a more sophisticated calculator. You can plot, you can build things, you can solve equations, you can solve differential equations, almost anything you want to do. You can try out with Maple. I just want to show you that I can, in Maple, when I want to assign a variable, I have to use a slightly different notation. So for Maple, the assignment is colon equals, so A equals 3. And didn't like that. It worked. Excuse me. It was just telling me what the assignment was. So there's the assignment, A equals 3, and now when I type in A, I get 3. I can also do B and assign that to be equal to 5. And again, type in B, it's 5. And now I can type in A plus B. And technically I should be using semicolons to tell it I'm ready to execute. And it executes 3 plus 5, gives me 8. As I expected. In this case, if I type in A and B adjacent, it expects AB to be another symbol. So I can give my variables any name I want, and so I cannot write multiplication by writing A next to B because the computer says AB must be a different symbol. So I can use the convention of A times B, and that works. One other interesting thing is that if I go back and change the value of B, if I say, oh, okay, well, actually I want B to be equal to 10, and then I go back and re-evaluate A times B, it will update the calculations for me. So just like in Desmos, it's kind of going along and updating as we go. In this case, it's nice because it's always reading from top to bottom, and I don't believe that I can go back and change the past. So this gives me a nice record of kind of my inputs, outputs, and so on. That's a really basic feature of Maple. Maple does all sorts of other interesting stuff. But for now, I think this is probably enough to get us going. So with that, I will end here and hope you have an entirely wonderful afternoon, and see you on Wednesday evening.